here this concept is okay. And our next is okay. Before going to the third point of the property, we see that if there is a enantiomer, how can we determine or we observe, we calculate that this isomer would have how many numbers of enantiomers, or any compound, let's suppose the same one as before. For example, sorry, here it is chlorine. So the basic idea is, how can we determine that a compound may exist in different number of enantiomers? So to calculate the number of enantiomers a compound may have, to determine or to calculate the number of enantiomers that a compound may have can be found out by Wandhoff's rule. Okay, and what is the Wandhoff rule? It states that maximum number of enantiomers a compound can have is equal to 2 to raise power n. And what is n? N represents the number of chiral or stereogenic centers. For example, in this compound there is only one stereogenic center, that is represented with asterisk. So the 2 to raise power n, where the n is equal to this chiral center, that is only 1, n is equal to 1, then the 2 raised to power 1 would be equal to 2. So as previously you have seen that it only has the 2 enantiomers. So in this way we may also calculate the maximum number of enantiomers that a compound can have. So the next property of enantiomers is they behave differently as they interact with other chiral compounds as well as the plane of polarized light. Because for example, the first, or if that compound exists as a 2 enantiomers, then 1 enantiomer would behave or would interact with plane of polarized light differently. The one enantiomer and the other enantiomer, for example, the one enantiomer rotates the plane of polarized light in clockwise direction, the other one rotates it anti-clockwise or counterclockwise direction. So in this way we say that they interact with the plane of polarized light differently. In the next lecture you will find the whole lecture about this plane of polarized light or the polarity or optical activity. Actually this idea lies under the topic of optical activity. Then you may find the whole lecture or the whole concept in the lecture of optical activity. So here we are studying their properties, that okay, they would interact differently with plane of polarized light in the way that, for example, one isomer rotates it, it means the plane of polarized light. So the one isomer rotates it in clockwise direction and the other isomer rotates it in anti-clockwise direction. And then the chiral compounds here, for example, this enantiomer interacts with the optical isomer of any other compound, and if this rotates in clockwise direction and the other optical isomer would rotate the plane of polarized light in anti-clockwise direction, what would be their net effect? That clockwise, anti-clockwise, so net effect would be 0. And in the other case, if it rotates in anti-clockwise direction and it also rotates in anti-clockwise direction, so their net effect would be enhanced, the signal would be so high. So in this way, they interact with the other chiral compounds differently. The enantiomers of the same compound, the compound is same, but enantiomers are different. In this way, they interact with the chiral compounds differently. And their very interesting and also very lively example is as maximum people, almost all of the people or in every age, they may suffer from any pain, and they have experienced the undertaking or the medication, undertaking the different pain relievers, for example, ibuprofen. Ibuprofen is a pain reliever and it is found in various drugs, in various painkillers and in various medications. So in different types of tablets or medicines, ibuprofen is present as pain reliever to help out the patients or to help out the public to kill the pain. So in the case of ibuprofen, one isomer is S ibuprofen and the other one is R ibuprofen. Actually, this shows whether they rotate the plane of polarized light along the clockwise direction and whether they rotate that along the anti-clockwise direction. So on that basis, they have a nomenclature to assign the R or S configuration, and in the next lectures you may find how to assign this R or S configuration. So among these two isomers or enantiomers, the only S ibuprofen shows the biological activity that is used as a pain reliever. So what is the formula? That looks like this one. So here CH2CH, CH3 and CH3, and here it is attached with COOH, then NH2, here it is CH3 and COOH and then hydrogen. So this is S ibuprofen and it is used to treat pain. So in this way we may say that their next property is the enantiomers have biological impact. So biologically the enantiomers are very, very important. So the S ibuprofen is only used to relieve the pain and the R isomers is inactive in this way. And the L-dopamine that is used to treat the Parkinson's disease, that is L-dopa, also called as L-dopamine, and L-dopamine or its L configuration or its R configuration, not the S or D, as The L and D systems and R or S systems are just to assign the configuration to the enantiomers. So in the case of dopamine, only R and L configurations are biological active. The other two are not used to treat the Parkinson's disease. So its structure formula is like this one. COOH, it is NH2, here it is H, and here it is attached with hydroxyl group. So this is the formula of L-dopamine. That is, this configuration system is actually based on this carboxylic groups orientation that would be studied in the next lectures. So here it is L-dopamine, and this compound is used as a drug to treat Parkinson's disease. So thank you very much for watching the lecture. The concept of optical activity would be taught in the next lecture. Please stay tuned and press bell icon. Thank you very much.